All right, good morning, everyone. Can you guys hear me okay? Okay. I put in the I just want to give you a couple reminders. Again, with the AP exam. Again, 36 Pro is technically not on the approved calculator list, but ideally you can have a graphing calculator. Bring that in case the proctors are asking you to put the 36 Pro away. But I would still bring it anyways in case you get to use it. So, for those of you who are not familiar with the graphing calculator, maybe when we start getting into the multiple choice portions, I can create a video or maybe have some help sessions along with a summary sheet for the 84 so that you're able to get accustomed to it if you're able to get your hands on one in time for the AP exam. Okay. Also, I sent out a reminder yesterday for you to contact Ms. White if you want to change your AP exam date from May 4th to June 9th. You want to take that digital version instead of the paper version face-to-face. That's in the gym May 4th. But also just know that the default is the May 4th date. So if you don't do anything or say anything, then you're going to be locked into that May 4th date. So if you want to change to that June 9th date, you have to contact her sooner rather than later, because there's a deadline coming up pretty soon where you're not going to be able to make that change anymore. So, or make that adjustment anymore. So if you're sure that you want to change to a digital date, then go ahead and contact her and let her know so that she's able to manually change that for you. Okay, any questions that you guys have with AP exams? All right, we're going to try to get through these two FRQs here. We have 1 and 2 on this back page. Okay, you're going to need your calculators. Okay, so number 1, a water tank at Camp Newton holds 1,200 gallons of water at time t equals 0. During this time interval between 0 and 18 hours, water is pumped into the tank at a certain rate. So the rate is given here. Keep in mind that this is a rate. This formula is not going to tell us the amount of water in the tank at a moment in time. It's going to tell us the rate at which it's entering into the tank. During the same time interval, water is removed from the tank at a rate of R of t, also gallons per hour. So part A says, is the amount of the water in the tank increasing at time t equals 15? So what we're going to do is we're going to evaluate W of 15 and R of 15 and see which one has the higher rate. Whichever has the higher rate is going to dictate whether the water level is going to be increasing or decreasing, right? If WT is greater than R of t, that means more water is flowing in at a higher rate than that's being removed. But if it's vice versa, where R of t is greater than WT, then we know there's the rate at which water is leaving is higher than the rate of water that's coming in, so we expect the water level to be decreasing. So we're going to compare those two values. Okay, so we're going to enter both of these into our calculator. Now, in your calculator, we have to understand how to deal with these this shorthand form. Much like how I would ask you to rewrite this if we're trying to find the derivative using chain rule, I will ask you to put that 2 outside a set of parentheses so that you know the outside versus inside function for chain rule. But here we just have to be able to enter this in the calculator. And much the same way, the calculator is not going to be able to handle this type of form, even though this is the way that shorthand form is the way that we write it. So if you want to enter this into the calculator, you got to write it out this way. And we use x's instead of t's, right? Parentheses, sine of x over 6, parentheses, parentheses squared. Okay, so this is how it's going to look in the calculator if you want to evaluate it. Okay, same thing here. Okay, so you're welcome to just enter 15 wherever you see the x, but because I know that I'm going to be using these expressions over and over again over the course of this problem, I went ahead and I entered in, I'm letting y1 and y2 store my w of t and r of t. Okay, so there's my w of t, and then here's my r of t. Okay. Make sure that you're in radian mode. We're always in radian mode. We're never going to have to, on the AP exam, you never have to switch back and forth, but always in radian mode. I'm going to go back to my home screen. I'm just going to call w parentheses of 15. So vars, y vars. Right now, y1 is holding my w of t, parentheses 15. That means we're going to enter 15 in for all the x's in the expression. We also want to find r of 15. So y2 is holding my r of t, 252. All right, so we see that the rate at which water is leaving is higher than the rate at which water is coming in. So we know that overall, at this moment in time, the water level is going to be dropping, right? So it says, is the amount of water in the tank increasing? So the amount of water in the tank, we can also think of it in terms of the amount of water coming in minus the amount of water being removed. Right, and if we get a positive value, that means water level is rising. If we get a negative value, we know water level is decreasing. So we can say since w of 15 minus r of 15 is less than 0, because here, let me write the value first. If I subtract those two values, it's actually going to be a negative 121. We know that's less than 0. So what that tells us is that the amount of water in the tank is decreasing at this rate at t equals 15. Okay, any questions with part A? Okay, part B says, to the nearest whole number, how many gallons of water are in the tank at t equals 18? So we know that the amount of water in the tank is dependent on three things here. Okay, it's dependent on how much water there's to begin with, how much water has been added, and then also how much water has been removed. Right. So all three piece of information is going to factor into how much water is in the tank at a given time. So I'm going to start off with a general formula, and we'll kind of build our way to a specific equation for us to, or expression for us to evaluate. So the total amount is equal to the initial amount plus the amount added minus the amount removed. So here's my formula that I can use. I can say A of t is equal to A of 0 plus however much I'm able to add in that time period from 0 to t. Right now, I want to have a general form so that I can adapt it for any situation. And then after I have a general equation, then I can put in a specific value for 18, for t equals 18. But the amount added, we know I have to involve integral because we can't just use W of t, right? W of t is gallons per hour, it's not gallons. So there's a mismatch in units if we just use W of t. We have to transform this W of t into gallons instead of gallons per hour, so integral is going to have to be used. And notation-wise, we just want to use a different variable from the variable up here. So when it gets entered in, it'll become t. So we just have to just choose a different variable here. All right, so here's my general formula that we're going to be using over and over again. But for our specific problem now, we can figure out how much water is in the tank at 18 hours. So the initial amount we know is 1,200 gallons. Okay, however much accumulates in that 18-hour period minus however much is removed in that 18-hour period. Okay, so I already have WT and RFT stored under Y1 and Y2. So as I create my integral, I'm just going to call these functions. My Y1 is holding W of t. So I go to vars, yvars, function Y1. Okay. Subtract out the amount removed. $1,310 gallons. All right, any questions for part B? All right, part C says, at what time t between 0 and 18 is the amount of water in the tank at an absolute minimum? So anytime we see absolute max, absolute min, we know that this is extreme value theorem. We're going to have to consider test endpoints and critical points. So we know what the endpoints are, right? Endpoints are just going to be 0 and 18, the amount of water at those time periods. But we also need to find critical points, and critical points comes from the derivative. So we're going to spend our time looking for those critical points. So critical points is found by setting a prime equal to 0. So before we can set a prime equal to 0, we first have to find a prime. To find a prime, well, we have our equation that we have built, and so we can work directly from here to build our a prime. Okay, so a becomes a prime, which is going to go to each term and take the derivative of each. A of 0, that's just going to be a constant. Constant will just drop out to be 0. We want to find the derivative of this expression. The derivative of this is going to wipe out the integral, leaving me with just w of t. And then the derivative of this expression is going to wipe out this integral. I'm just left with r of t. Now that we have our derivative equation, we're going to set equal to 0. Okay, so you can either use numsolve on 36 Pro to plug this in and find a solution, or I'm going to use my graphing calculator. I'm going to graph this expression. And I'm going to look for the x-intercept. Okay, because wherever this graph crosses the x-axis, it's going to be the solution that I'm looking for. These are the critical points that I'm going to be ultimately trying to target. So I'm going to graph this here. I go to y equals, I'm going to do wt minus r of t, but rather than typing everything out again, I'm just going to call them and just say, okay, I want to graph wt minus r of t, but basically is y1 minus y2. Something else I want to point out is you may come to a cross situation where you have multiple functions entered in, and then the equal sign are all being highlighted. So if you have equal sign highlighted, that means when you hit graph, all these graphs will show up. And if you only want to see one graph, or if you don't want to see every graph that you have entered in because maybe you want to save it for later, or you want to be able to call it, what you can do is you can scroll over to the equal sign, hit enter, and then you can deselect it. You can unhighlight it. And if you unhighlight, it's still in the system, it's still in the calculator, but it's not going to show up in the graph when you hit graph. So I only want to see this y1 minus y2. I only want to see wt minus r of t because I don't want all these other graphs to kind of get in the way of me being able to read it correctly. So I'm only going to highlight that y1 minus y2. All right, I'm going to look for the x-intercept. I'm going to graph it, but I like to just kind of have a starting point of zoom 6. It'll kind of give me a standard window. Right, now, the standard window is most likely not going to be enough because if you look at the expression here, these are pretty high numbers. So our graph is going to be stretched out into the hundreds where we may be zoomed in a little bit too far. But let's just see where we are. I want to kind of show you what it looks like if something is zoomed in too far. So zoom 6, hit enter. All right, so this is an indication that you're probably looking at a graph that is you're looking at it too closely, that you're not getting a good perspective. When you see a vertical line, that means that you're zoomed in a little bit too far in. We want to zoom out so we can kind of be able to see a curvature with our graph. So we're going to have to go to Windows, and we have to play with our bounds. So you're only going to play with 4 values here: x min, x max, okay, and then your y min, y max. Okay, so that just means how far left and how far right you want your axis to go. Now, I know my boundary is from 0 to 18, so I'm just going to do values slightly to the left and to the right, just so I can see around my corners there. And here, let's just play with numbers, right? We know that these are in the hundreds, so I'm just going to arbitrarily choose -200 to 200. You can really just try different values in the same range and see if it's enough for you to get a good read on the graph. That's all we care about. We just want to be able to see so that we can trace the graph and actually see a curvature and be able to kind of follow the path of the graph. Okay, so I just chose some arbitrary numbers in the range of what I see here. Okay, graph. Now you see that if I want to see the full graph, I'm not really seeing the top, right? So technically I should have maybe expanded a little bit further up to maybe 250 or something, but that's not really important because all I care about are the x-intercepts, right? I only care about the x-intercepts. So this is enough for me to trace where I don't feel like I'm looking at a vertical line. So I'm just going to look for these 2 x-intercepts. Second trace, select 0. Now I'm going to choose a point to the left of the x-intercept, hit enter, scroll over to a point on the other side of the x-intercept, hit enter, and now it's going to zoom in on that x-intercept there, hit enter again. Okay, so t equals 6.495. I'm going to find this other x-intercept as well. So I got to go back to second trace, select 0 again. Okay, so here's a point to the left of the x-intercept, hit enter. Choose a point on the other side of the x-intercept, hit enter. Okay, 12.974. Or 975. So now we have our critical points and our endpoints identified. So now we can plug them all into the original amounts equation and figure out which one is the lowest, which produces the lowest value. Okay, so we'll list out all of our candidates here. Right, so all of them go into this equation that we've already built that can adapt to any time period. So A of 0, 1200. We know that's going to be, we're done with that. 6.495, we just have to figure out how much is added and removed in that time period. And then A of 18, we have that from part B, so I'm just going to copy that down, carry that over. Okay, so we have to just plug these in. Now I already have my expression for A of 18, so I'm just going to go back to that entry, and I'm just going to change my bounds, just so that I don't have to retype everything. $525 gallons. If you do, you can either scroll up to that point, or you can do second enter. If you do second enter, it'll recall the previous entry that you just did. Okay, 16.1697. So we're looking for the absolute minimum. So amongst these values here, the smallest value that we see is 525. So there's our absolute minimum. Okay, any questions there? Okay, let's look at part D. It says for T values greater than 18 hours, no water is pumped into the tank, but water continues to be removed at the rate of R of T until the tank becomes empty. Let K be the time at which the tank becomes empty. Write but do not evaluate an equation involving the integral expression that can be used to find the value of K. So right now we're concerned about how long will it take from hour 18 until K when there's no more water in the tank. And we know that R of T is still in effect. This is still the rate at which water is being removed. But we want to know how much water to remove so that we can stop, right? We know that there's no more water coming in, so however much water is in the tank at 18 hours is however much we have to remove. So we know A of 18 is 1310, so we already found that already, so we're going to just insert that here. So that's all we need to do, just set up an equation. We know that there's 1,310 gallons for us to accomplish, so once we can figure out that K value that will make this expression equal to 1310, we know that's how long it's going to take for the tank to work its way down to become empty. Okay, any questions with number one? Okay, let's turn to the back page, number two. All right. Before we go into this problem, I just want to kind of talk about how there's a range of difficulty with FRQs. Not all FRQs are going to be the same level of difficulty. There's some that are just easier than others. There are some that are more difficult than others. And so this falls into the range, I think, of a more difficult one, especially part C. That's kind of hard to get through it, or there's a lot going on. So I want to kind of talk about that. You don't have to get every part of an FRQ to be able to earn a good score on the AP exam. Okay, typically what happens is, A and B are easier than C and D, right? So the difficulty kind of ramps up as you get further down into FRQ. But you can use that to your advantage as well, in the sense that if you're stuck on the problem where you have an idea, you've made some notes, but it's going to take some time for you to maybe process it, you can always kind of circle it and then move on to the next problem, and tackle all the easier parts of every problem, and then you spend your remaining time trying to earn points with the more difficult problems, right? So that's something I don't think you'll be able to do on the digital exam, but at least on the paper exam, within a section, you can move between FRQs and be able to kind of pick and choose the problems you want to work on first. So, but yeah, just wanted to kind of talk about how there's going to be some problems that you're not going to be able to make much progress on, but it's okay, because as long as you can try to just earn as many points as you can. It's not all or nothing, right? It's not like you earn everything or nothing. There's always these partial credit that you can earn across these FRQs. So, don't get stressed out if you are not able to answer, part C or D of a problem. I would say put a star next to it, move on, work on something else, and then come back to it at the end. Okay, so let me read this problem here. There's no snow on Janet's driveway when snow begins to fall at midnight. From midnight to 9 a.m., snow accumulates on the driveway at a rate modeled by F of t, cubic feet per hour. So this is a rate where t is measured in hours since midnight. Janet starts removing snow at 6 a.m. The rate g of t in cubic feet per hour at which Janet removes snow from the driveway at time t hours after midnight is modeled by g of t. So let's talk about what this means. So right now this seems kind of abstract, right? What is this telling us? I want to kind of give a more concrete visual as to what's being accomplished here. So this is telling us the rate at which Janet is removing snow. But we have to understand that this is a rate, right? This is in terms of cubic feet per hour. All these values are cubic feet per hour. But the nice thing is that these are all constant values, so we know exactly how much she accomplishes in 1 hour, or in these in 1 hour blocks. Okay, these are all cubic feet per hour. So we know that up until 6 a.m. She hasn't begun to shovel snow, so nothing has been accomplished up to that point. But then between 6 and 7 a.m., she's going to be working at 125 cubic feet per hour. So in that 1 hour period, because it's 125 cubic feet per hour, she's going to remove a total of 125 cubic feet of snow in that 1 hour period. And so, by the time we reach 7 a.m., she would have accomplished or completed 120 or removed 125 cubic feet of snow. Now, the next 2 hours, she is slowing down a little bit. The rate is not as fast as before, but 108 cubic feet per hour. But over the 2 hour period, we know that by 9 a.m., she's going to remove another 216. Right, 108 times 2. So we know that all in all, over this 3 hour period, she's going to have 341 cubic feet of snow removed in total, right? So I just want to kind of we may not use everything here, but I want to kind of bring this out of the abstract and into something that that makes sense and visually, and you can kind of see it in motion. Okay. All right, so part A says how much snow has accumulated on the driveway by 6 a.m. So this is before Janet starts to shovel snow. So we know this is completely dependent on this f of t, on the rate at which snow is falling on the driveway. But we have to make some adjustment, right? We can't just enter 6 into f of t, because then we're getting something in cubic feet per hour. We want total cubic feet of snow. So we want to be able to convert something that is cubic feet per hour into cubic feet. So we got to go through integral, right? We want to accumulate this rate over the 6-hour period to figure out how much snow has accumulated on the driveway. I already have f of t stored under y4. So I'm just going to call this as I take the integral. Okay, you should have gotten 142 cubic feet of snow. All right, part B. Part B says find the rate of change of snow, volume of snow on the driveway at 8 a.m. So what we're going to do is we're going to figure out what the rate of snow falling versus the rate being removed, right? And whichever has the higher rate, we're going to know whether there's more snow accumulating at that moment or whether the volume of snow is decreasing on the driveway. So I'm going to find the rate at 8 a.m. where that snow is falling at 8 a.m. So I'm going to plug 8 into the function. Again, I already have f of x stored under y4, so I'm just going to call y4 and parentheses 8. That's just going to enter 8 into all the variables. So f of 8 is 48. So snow is falling at 48 cubic feet per hour at 8 a.m. But then at 8 a.m., Janet is removing snow at 108 cubic feet per hour. Right, 8, this time interval here. And we can tell that g of 8 is greater than f of 8, so we know that more snow is being removed than the rate that is falling. So we know overall the volume is going to be decreasing. All right, so we can say the amount of snow on the driveway is dependent on how much is coming down versus how much is being removed. And if we get a positive value, we know that there's more snow being added to the driveway. But if it's a negative, we know there's more snow being removed from the driveway, that the volume is decreasing. So f of 8 minus g of 8 is going to give us a negative value. So to put this into words, we can say the amount of snow on the driveway is decreasing Okay, so the negative indicates that the volume is decreasing, so the amount of snow on the driveway is decreasing at a rate of 59.583 cubic feet per hour at 8 a.m. Okay, so far, I think this has been manageable. Part C becomes a little messier here, so let's look at Part C. Part C says, let H of T represent the total amount of snow in cubic feet that Janet has removed. So here, H of T is not going to be considering the amount of snow falling. It's just with the progress that Janet is making with removing snow from the driveway. All right. So we know that there's nothing's going to occur between 0 and 6, so there's nothing to worry about there. But things begin to pick up between 6 and 7 a.m. So something that I want to kind of have as a kind of a rearranging of our formula is that the total amount, okay, is going to be kind of the pickoff point, however much has been accomplished up to that point, plus the amount removed, the progress made in a second time interval. So we know that for values between 6 and 7, or for time period between 6 and 7 a.m., the total amount, okay, is going to be however much is accomplished at 6 a.m. And we know that up until 6 a.m., nothing is accomplished. We know this is going to be 0. But then between 6 and 7 a.m., we're going to have some percentage of that 125 cubic feet of snow being removed. Now, this range is only going to be between 6 and 7, but we want to give it that flexibility where I can find the amount of snow removed if it's 6:30 or 6:25 or 6:15. So I'm going to leave it as a T to give it that flexibility. Okay, so now I'm going to create an equation out of this. H of 6 means however much is has been shoveled at 6 a.m. and nothing has been accomplished yet, right? It's only after 6 a.m. does she begin to start making progress. So we know this is going to be 0 for H of 6. And then we're going to take care of this integral here. We're going to go through power rule. 125 becomes 125x. And then we evaluate our bounds between 6 and t. Plug in our upper bound first. And if I factor the 125 out, so now this is going to give me a percentage of that 125, right? If I know if it's 7 minus 6, that's going to be a complete hour. So a complete hour is going to be exactly 125 cubic feet. But if it's only a half hour, then it's only be half of that. If it's only a quarter, if it's only 15 minutes, 615 minus 6, that's just a percentage of that 125. Okay. Now between 7 and 9 a.m., we have a different set of rates, right? So we're going to create our equation, H of t equals. Now the initial amount means at 7 a.m., she's going to have already 125 cubic feet taken care of, right? So we know that there is an accomplishment up to this point. So H of 7 is going to be 125. And then we can worry about the progress from 7 a.m. forward. So if I want to figure out how much snow has been shoveled at 8 a.m., I know it's going to be 125 plus however much I accomplished or she accomplishes in this time period. Okay, we can go through a power rule here. 108 becomes 108x. Evaluate between 7 and t. Upper bound first. If I can work this out, but it's just easier if I just factor the 108 out. It's just easier to work with here. So total, between 7 and 9, she's going to have this amount, 125 plus 108 t minus 7. So to put it all together, this is how much snow she is going to accomplish, or how much snow she is going to be able to finish doing at any moment in time. We know 0 for values for time between midnight and 6 a.m. But then between 6 and 7 is going to be a percentage of that 125. And then from 7 to 9, it's going to be 125 plus the percentage of what she accomplishes in the two and whatever time period between 7 and 9. Okay, so that's part C. Okay, and finally, part D. How much snow is on the driveway at 9 a.m.? Okay, so now we have to consider the three things involved here. How much snow in the beginning, how much snow has been added from snow falling, and then how much snow has been removed. So we know A of t. Initial, there's no snow at midnight. And then the amount added, we know is the integral from 0 to t of f of x. And then the amount removed, there's no more need for integral here because h of t is exactly in terms of cubic feet. So we can just do h of t. So the integral is needed for f because f is standing at cubic feet per hour, but h of t has been transformed to be cubic feet. So now we can find a of 9. So 9 a.m., I can plug 9 into here, and that's going to be exactly what we found here, right? We know that in that 3-hour period, she's going to accumulate 341, so we're going to get that here. Plus, we use the calculator to find how much snow has been added, and now that's going to tell us exactly how much snow remains on the driveway. Okay, any questions there? Okay, let me just talk about tomorrow for a quick moment here. Tomorrow, I would like for us to go through this differential equation problems worksheet. However, I'm getting my hold on a second. Okay,